Hi there, I'm Colton,
I'm Kylie.
and today we're going to be talking about how a continuous charge distribution creates an electric field.
So first thing you do, we'll just explain really quickly how to do it and then we'll do an example and a real life example. So first thing, you draw a line from the rod to the electric field and you want to make sure to label your DQ off-centered from the origin on the rod so that theta is greater than 0. And then theta is also the angle between the line you drew and the electric field.
Next, we're going to use the Pythagorean theorem in order to calculate the length of the line drawn from the rod to the electric field. So if this is our rod and our electric field is not always perfectly perpendicular, then we could use trigonometry in order to find the distance from our charge on the rod to the point of interest, the point where there's an induced electric field.
Next thing you do is you replace the variables in the equation. The electric field equation, electric field equals 1 over 4 pi E naught times charge over r squared. And you want to write that equation as an integral because the one that I just described is the electric field at a point, whereas the integral is going to give you the total electric field. So you actually want to replace your variables for the equation, the integral 1 over 4 pi E naught times dq over r squared. And then dq is equal to lambda dx, or dq is equal to lambda dy.
And since electric field is a vector and not a scalar, we're going to have to break it into components, and we can do that by multiplying it by either cosine theta or sine theta, depending on how you set up your integral. It can be either for the x or y components.
And then lastly, you just replace cosine and sine theta or sine theta with the trig identity because you just want one variable in your equation when you're integrating. So you replace it with adjacent over hypotenuse, for example, for cosine theta, and the hypotenuse would be root x squared plus y squared, for example, in this equation. Also, the x term, the x component of the electric field vector isn't always cosine theta because it does depend on where the theta is in your picture.
Now let's do an example. Now to envision this as a real world scenario, we're going to take a rod and charge it by plugging it into the wall. And now since charge is running through it, we know that it's going to create an electric field at a nearby point. And now we're going to calculate what that electric field is going to be.
We're back with our real life example of the rod and the point charge. So here we just drew a little picture of what you saw before where Colton was holding the rod and then the lollipop was the point charge. Here's the lollipop and then here's the rod. We picked an infinitesimally small DQ, which is just a small charge on the rod that we're going to be measuring the distance r from the point to that charge. Theta is the distance between the point, the angle between the point and our infinitesimally small dq. L is the length of the rod. Y is the y component of the distance between the point and dq, and x is the x component of the distance between x and dq. Then when we move over here, here's our equation that we talked about from the last time you saw the whiteboard. We plugged in r, dq is lambda dy, because dq is on the y-axis, and then and then that's it.
The reason that we can equate dq to lambda dy is because dq is our infinitesimally small point charge on our rod, and dy is an infinitesimally small length of our rod, and lambda is our charge density, meaning it's our charge per length. So by multiplying charge per length times our infinitesimally small length, we will get dq. And we estimated that the charge of our rod is about 6.022 times 10 to the 23rd coulombs, and that the length of our rod is about 0.30 meters. Therefore, our lambda, or charge density, was about 2.0 times 10 to the 24th coulombs per meter. Next, since electric field is a vector, we need to break it down into components. And here we have lambda dy over r squared, because dq is equal to lambda dy in this case. And since it's our x component, we know that it's going to be cosine theta, because if we're looking at this, cosine is adjacent over hypotenuse. And we can rewrite that over here, plugging in lambda, and we still have dy because that's what we're integrating with. And r squared is just going to be the square root of x squared plus y squared squared. And we can rewrite cosine theta as x over square root x squared plus y squared, because x is our adjacent and root x squared plus y squared is our hypotenuse. And we don't want theta because we don't want to integrate with theta. Otherwise you would need a double integral. And the bounds of our integral are negative L over 2 to L over 2, because you start down here, which is half of the way down our rod of length L, and then we make our way all the way up to the top, and that's assuming that we're setting this y value to 0. And for the EY, you would do the same thing except with sine theta in order to get this component of the electric field. And instead of x over square root of x squared plus y squared, it would be y over square root of x squared plus y squared. And then you could plug these in and evaluate the integral, but the professor will not ask you to do that.